Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. Select the lightest W-shape section from W690, W610, and W530 sections only that will carry a concentrated load at the center of 150 kilonewtons of the beam with a simple span of 9 meters subjected to the following restrictions: allowable bending stress of 140 megapascals and allowable deflection of L over T60. Also compute the maximum actual bending stress and maximum actual deflection after selecting the W section. So here are the selections from the table tips of the book by Pitel and Cusalas. So for the solution for bending, assuming bending controls, so allowable bending stress 140, bending stress is moment over section modulus. The maximum moment is PL over 4, P150 length 9 over 4. So PL over 4 maximum moment when the beam is loaded with concentrated load at center. So it is 37.5 kilonewton meter. Then we can now compute the required section modulus from bending stress equals moment over section modulus. So 140 must be greater than moment in kilonewton meter times 1000 squared to convert that to Newton mm divided by section modulus, so that section modulus should be greater than equal to, the units is in mm cube. So S should be greater than 2411 times 10 to the 3 mm cube. Now, this must be satisfied as well as the moment of inertia for deflection. So let's compute because there are two restrictions here. So for deflection, the deflection is PL cube over 48 EI, and the allowable deflection is L over T60. So L over T60 should be greater equal to PL cube over 48 EI. Cancel out L, cross multiply. So 48 times E, 200,000 megapascals, I in mm to the fourth over T60 should be greater than 150 L square because we cancel L. Then kilonewton meter square is kilonewton meter square. To convert that to Newton mm cube, Newton mm square rather, we multiply 1000 cube to be consistent with the left, so that I is in mm to the fourth. So the required moment of inertia should be greater than equal to 455.6 times 10 to the 6 mm to the fourth. So let's now check for the W690 by 265. The lightest is W690 by 125 in this table here, and I is too high. It satisfies, but it's too high, as well as for section modulus, it also satisfies. So W690 by 125 satisfies. So take note, this 125 here is 125 kilogram per meter. So let's proceed to W610. There might be a lighter section which satisfies these conditions. So this is also same as that 125. I satisfies, section module satisfies, but there are lighter ones that satisfies. So 113 satisfies, section modules is 2880. 101 762 is greater than 455.6 times 10 to the 6, so this section satisfies. 2520 is also greater than 2411, so the lightest so far for W610 is W610 by 101. So we reject W690 because 125 is heavier. While W610 by 92 I satisfies, but for section modulus it does not satisfy. This is only 2150. The required is 2411. Now for W530, the lightest so far is 101. So let's proceed to 101 here. I is 616, so it satisfies, but the section modulus 2290 less than 2411, so it does not satisfy. So that means we rise this one, W530 by 109, satisfies both moment of inertia and section modulus, but it is heavier because it is 109. So therefore, this is the lightest W section that will satisfy both, and this is the most economical section. Therefore, we select W610 by 101. So the answer, select W610 by 101. The actual moment of inertia is 762 times 10 to the 6, which is greater than the required for 55.6 times 10 to the 6 mm to the fourth. The actual section modulus is 2520 times 10 to the 3 mm cube, which is greater than the required 2411. So that's why this is the lightest section. Now, the weight of the beam is 101 kilogram per meter. That will add stress and bending stress maximum at the center, and it will also add deflection. So let's convert 101 kilogram per meter to kilonewton per meter. 101 kilogram per meter times 0.00981 kilonewton per kilogram. So the uniform weight of the beam is 0.9908 kilonewton per meter. So the actual moment, because the maximum actual bending stress is actual moment over actual section modulus. So the actual moment is 337.5 plus weight of beam length square 9 square over 8. The moment contributed by the weight of the beam itself. So moment actual is equal to 347.53 kilonewton meter. So therefore, we can compute the maximum actual bending stress moment times 1000 square to convert it to Newton mm divided by section modulus of 2520 times 10 to the 3 mm cube. So the result would be in megapascals. So maximum actual bending stress is 137.9 megapascals, which is less than the allowable bending stress. So that's why it's safe. For actual deflection, it is PL cube times 1000 to the fourth to convert that to Newton mm over 48 EI. So that will be in mm plus 5W of beam L to the fourth times 1000 to the fourth to convert it to Newton mm cube over 384 EI. So that will also be in mm. So this is the deflection due to the concentrated load at the center, PL cube over 48 EI. Deflection due to the uniform weight of the beam, 5W L to the fourth over 384 EI. Combining, the actual deflection is 15.5 mm, which is less than the allowable deflection of 9,000 mm, 9 meters over 360, which is 25 mm. So that's why it's also safe. So that's it for this problem. I hope that you were able to follow and understand the explanation and solutions.